So chemical bond. We have to look at the way atoms come together to make molecules or compounds. Now there's two giant categories of compounds that we're going to be talking about. And I'm going to give you lots of examples. These two giant categories of compounds have separate rules for naming them. They have separate ways of bonding and coming together. And you have to make sure that you understand the two separate compounds, separate sets of compounds, because this is going to carry through the rest of the course, that we treat these two silos of information independent of one another. All right, so that will begin our discussion of chemical bonding. So core electrons are the ones that are the ones closest to the nucleus. Remember when we talked about electron configurations last week? We decided that core electrons were the same as the noble gas configuration. So when you're doing the shorthand version of electron configurations, you could put the core electrons, the noble gas directly preceding that element, in square brackets, and that's the core electron. So in terms of a definition or vocabulary word, core electrons are the innermost electrons where all of the shells and subshells are full, aka noble gas electron configuration. Valence electrons are in the outside, generally they're S and P subshells, and the valence electrons are the ones we care about, and that's why we talked about the charge and how many valence electrons last week, because remember that's where the action is going on. Electrons are either moving back and forth between atoms, being shared, they're moving back and forth, being donated and accepted, or they can be shared between atoms. They all do so. They all either lose electrons, gain electrons, or share electrons in order to achieve this idea of the octet rule. And if we could assign anthropomorphic characteristics to inanimate objects like atoms and molecules, we would say they want to achieve this octet. Of course, atoms and molecules don't have a brain or a central nervous system, so they can't want anything. But what really is true, if you talk to a chemist or a physicist, is that these atoms and molecules look to achieve the octet because that's what they call the lowest energy state, right? In nature and in science, substances strive to reach the lowest energy state because they're not expending a lot of energy existing like that. So the two big categories, and this is where we need to keep them separate from each other, is ionic bonds versus covalent bonds. All right? Ionic bonds are metal, non-metal combinations. Covalent bonds are exclusively non-metal combinations. So if we look at a copy of the periodic table, I'm going to borrow yours right here. Look at a copy of the periodic table, remembering that metals and nonmetals are differentiated by the stair-step line that starts to the left side of boron. I'm going to draw that in on your periodic table for you. No charge. Metals are on this side, nonmetals are over here. So ionic compounds, you take something from this side and something from this side, and you bond them together. That's an ionic compound. We call it an ionic compound because it's made of ions. Metals lose an electron when they make these kind of bonds, right? Because metals have usually one or two valence electrons, and if they lose those one or two valence electrons, they reveal a full inner shell which has the octet. Then the nonmetals gain the electron that the metal gives up. So it's a match made in heaven, right? These guys want to give up electrons to achieve the octet. These guys want to grab electrons in order to achieve the octet. And that's where the charges from these things come from. Now, when you look at the charges of the elements by group, that doesn't mean they always have that charge. That just means that when they do form ions, they form ions with that particular charge, right? Normal lithium has no charge. Ground state lithium has 0 charge on it. However, it has that one valence electron. When it loses it, it becomes an ion with a +1 charge. So I always have students write a little +1 at the top of that family column, the alkali metals, in order to know that those ions, when they do form ions with a +1 charge. Sort of like that commercial. You know, the most interesting man in the universe? What kind of beer does he drink? Dos Equis. Now, he doesn't always drink beer, right? Okay. These don't always make ions. But when they do, they make ions with a +1 charge, right? Okay. So that tagline will help you remember. I know sometimes my jokes are lame and silly, but they help you remember. The second group, those are always ions with a +2 charge. Now, why do you suppose they form ions with a +2 charge? They're in the second group, which means they have how many valence electrons since they're a representative element? They have 2 valence electrons, which they lose both of. They don't make +1 ions. They always lose both electrons. Now, once again, they don't always form ions. Normal strontium has a 0 charge. Ground state strontium is 0 charge with 2 valence electrons. However, if some nonmetal comes cruising by and goes, hey, strontium, those valence electrons of yours are looking mighty fine. Strontium goes, well, you know what? You can have them. I don't want them. And let's bond. So those are always, they don't drink Dos Equis, they drink Coors Light, right? They don't always drink beer. But when group 2 ions drink beer, they drink Coors Light. There's only 4 others that have a 4 other metals, I should say, that have a particular ionic charge. That's aluminum, which is a +3. I want you to put a little +3 in aluminum's box. Zinc and cadmium are +2, and silver is +1. Those are the groups, metals that always have a single ionic charge, which means they only make ions with that charge. These only make ions with +1, these only make ions with +2, +3, +2, +1. All of the other metals, meaning everything to the left of the stair step and up to this box, so the things that you see I just colored in, with the exception of those 4, can make more than one kind of ion. They can make +1 ions, +2 ions, +3 ions, sometimes even as much as +4 ions. And you have to know on a case-by-case basis. But it's super helpful to say those are always +1 when they make ions, those are always +2, +3, +2, +1. Some of the other non-metal families, because these ones are giving up electrons and these ones are taking it in ionic bonds, the non-metals always have a particular charge. Now the halogens, they don't form ions, so we say they are always at ground state, right? Or, excuse me, the noble gases, the noble gases. The halogens, on the other hand, have how many valence electrons since they're in group 7? They have 7. They want how many? 1 more. Sorry. They want 1 more. So when they form ions with a -1 charge. So put a little -1 above the halogens, because you know those ions always form ions with a -1 charge. Oxygen, sulfur, this group here, since it's in group 6, how many valence electrons do they have? 6. How many do they want? 8. They want 2 more, so generally they form ions with a -2 charge. So that's super helpful to know that this is generally -1, those are generally -2, and the other ones happen. Now, when ionic compounds form, they make something that looks like this. That's kind of hard to see from the background there. All right. It is a repeating crystalline structure. This particular one happens to be calcium chloride, I believe. No, it's cesium chloride, so I think it's a 4-to-1 ratio. The gray balls represent the chlorine, and the green ones represent the cesium. The bars in between, we're going to be talking about these today. Are they really bars like that in between the atoms in real life? No. What do the bars represent? A bond. And what makes a bond? Sharing electrons or donated and taken electrons. So the bar is represented by a pair of electrons. It takes 2 electrons to make that bar. And they can't really symbolize 2 electrons zipping around, right, and hold the thing together. So they use a bar to show it. So that's what ionic compounds look like. If you were going to draw on paper what an ionic compound look like, good old sodium chloride. Remember you guys used sodium chloride in your lab last week? And you looked with a magnifying lens at the individual sodium chloride crystals, or was that this week's lab? That's this week's lab. All right, those of you that did lab on Monday, what do the crystals look like?
Little cubes.
They look like little cubes, right? Cubes. Okay, now I'm not the best geometry drawer, but if you look, they look like little cubes, and the reason they look like little cubes is because it's a repeating structure of sodium and chlorine that happens in these nice little cubic structures. And when you break them, they break exactly along the planes of the cube, and they make smaller and smaller cubes of sodium chloride. So we say that for ionic compounds, we have this lowest unit. We abbreviate ionic compounds something like this, NaCl, we know is sodium chloride, you guys have seen that before. And that's the lowest whole number ratio. So the lowest whole number ratio of atoms in the compound. So we're still talking about ionic compounds. Ionic compounds, chemists like to abbreviate, and we call all ionic compounds a salt. And you go, wait a minute. I thought sodium chloride was salt. It is. It's table salt. But all ionic compounds to chemists are salts. So how many do you think you could make? If it's anything from this group and anything from this group, maybe hundreds, maybe thousands of different combinations, right, of ionic compounds. So there's literally thousands of different kinds of salt in the world, and that's why the ocean is so salty, because a lot of the salt that's on the ground is soluble. It will dissolve in rainwater, it runs down to the ocean, and it has all kinds of salts, not just sodium chloride. It has magnesium chlorides and all different kinds of salts. So if you're at the dinner table with a chemist and you say, pass me the salt, you're being really ambiguous. You say, pass me the table salt, or pass me the sodium chloride, right? There's another type of salt. Does anybody know what the common name for this kind of salt is? Not the technical name. The technical name is calcium chloride. But what's the common name for this? If that's not sea salt. Good question. There's a whole bunch of stuff in sea salt. Good guess. We don't use this in Arizona much.
Oh,
road salt, right? Okay. That's road salt. They don't even use this in Flagstaff. In Flagstaff, you know what they use when it snows? Cinders. Cinders from the volcanoes. Because the cinders don't go into solution, they don't make your car rust, they don't do all the funny chemical things to them, and they also help attract the sunlight because they're dark and they help melt the snow that way. So it's a different thing that road salt does. All right, so all salts are any ionic compound in terms of how you're going to name it, and it's a metal-non-metal combination. Covalent bonds, on the other hand, are formed with a sharing of electrons. So ionic bonds, the metal gives them up, the non-metal takes them. That's why it's called ionic, because when the metal gives up electrons, it becomes positively charged. When the nonmetals take them, they become negatively charged. So it's a formation of bonds between ions, therefore called an ionic bond. And they make these big crystalline structures that we can't put Na437Cl 437, right? We just put the lowest whole number ratio NaCl. Not so of covalent bonds. Covalent bonds, there's much fewer of them, because we only can choose from non-metal combinations. And because they're all greedy for electrons, right? Non-metals all want extra electrons. They want to grab them from somebody else. They have to share their valence electrons. So ionic bonds transfer. They go from the metal to the non-metal. Covalent bonds share, and the electrons will spend time around both of the atoms in between the bond. If we wanted to look at examples of what things are covalently bonded, they're not big, giant crystalline structures like salts. They're discrete little molecules that can exist on their own. So this is, does anybody have any idea what this molecule is? Not water. CO2. Carbon dioxide. This is a molecule that can exist on its own in the air, right? It's floating around the air right now as we breathe. You are exhaling carbon dioxide. Each of those individual molecules can exist as an entity on itself without having to be bonded to a whole bunch of other things in a crystal structure. This is methane gas, fart gas, greenhouse gas. You know what the biggest producers of methane gas are on the planet? You'd think so. But it's not. It's a much smaller creature, but it has the same digestion as a cow. Cows have to ferment. That's why they have all those stomachs. They have to ferment the grass before they can digest it. It's a very small insect that has that particular type of digestion. I don't think it's a beetle. It's termites. Termites actually are the biggest producers of methane gas, which is a greenhouse gas on the planet. Now, if we could figure out how to harness methane gas, it's very clean burning gas. We could take it out of the atmosphere, right? So maybe we just need to figure out a way to get it directly from the cows or the termites into a tank. Don't know. All right, so these are molecules that can exist on their own. If they're in liquid state, they're not bound to each other. They're just rolling around and having motion in this direction. If they're in gaseous state, they're vibrating, they're rolling around, and they're translating. But they all exist as independent entities on their own without having to be bonded to a crystal structure. And that's why they share electrons versus grabbing electrons. All right, so ionic bond is metal-non-metal combination. Metals give them up, non-metals take them. That's what holds the whole thing together, because one thing is positively charged, one thing is negatively charged, opposites attract. Ionic bonds, there's a good picture of an ionic bond. That looks like NaCl. Now, you guys could predict, I'll bet at this point, which one of those is Na and which one is Cl. Look at the periodic table, see where Na is, see where Cl is. They're in the same row, right? They're in the same row. Who's going to be bigger, Na or Cl? Na or Cl, who's going to be bigger? Na is going to be bigger, right? Because left to right, it gets smaller. So Na is going to be bigger, but once it becomes an ion, what happens to the size of the atom? Na is going to do what? Shrink a bit. Cl is going to get bigger a little bit because it's going to gain electrons. All right. So cations are formed, anions are formed. We've already talked about particular charges in them. And now we already talked about electron dot formula structures, and we looked at the different areas where you're going to put electron dots. That's going to lead us to this idea of, we already talked about atomic radii, covalent bonds. Now, the next topic is this idea of molecular geometry. When we talk about something that is an ionic bond, we talk about the crystal lattice structure. We're not going to discuss the structure of crystals in this class. When you get to Chem 151, we talk a lot about crystal lattice structure, all right? We have face-centered cubic, body-centered cubic, all this kind of good stuff. But we're not going to really discuss that in this class. What I want you to know is that ionic compounds form large crystal structures of repeating atoms and ions in a very rigid formation, okay? What we're going to be talking about now is molecular geometry, meaning when these molecules come together to make, or when these atoms come together to make molecules, they come together in a particular way that is geometric in nature. All right, so we've got, so now we're talking in general about covalent bonds. So let's get a new piece of paper here. Talk in general about covalent bonds. All right, it's covalent bonds. Remember, these are the true molecules. When we talk about an ionic compound like sodium chloride, we discuss the individual unit as a formula unit. It's the lowest whole number ratio of the stuff that's in there. Covalent bonds is a true molecule. It's the actual number of atoms involved in the compound. So you don't reduce it to its lowest whole number ratio. You talk about the actual numbers of atoms involved. Covalent bonds can be polar or nonpolar. So in general, what does polarity mean?
It's like attracted toward.
Like a magnet, sort of, or the Earth has poles, right? There's positive and negative ends to it. So a polar molecule is going to have a positive area to it and a negative area to it, the molecule itself. A nonpolar molecule is going to be the same all the way around. And what causes the polarity? It has to do with how the electrons are shared. Because remember, in covalent bonding, electrons are shared between atoms. Okay? So for example, if we look at something like good old H2O, right? Let's look at the individual dot structures for both hydrogen and oxygen. Well, you look at oxygen here. How many valence electrons does oxygen have? 6. So we're going to do the Lewis structure just for oxygen. 1, 2, 3, 4, 5, 6. Now, it turns out these individual Lewis structures are super important because the bonding pairs, or the paired electrons, generally you're not going to be able to make a bond there. Okay? The only place you're going to be able to make a bond is where there's non-paired electrons. So oxygen, it turns out, has 2 opportunities to bond with something else. It cannot bond there, it cannot bond there, but it can at those 2 locations. If we look at the Lewis structure for hydrogen, how many valence electrons does hydrogen have since it's in group 1? Single valence electron. So we got 1 hydrogen there, 1 hydrogen there. All right. I see an opportunity here between hydrogen and oxygen to form a partnership where they share electrons and everybody has 2 in between them. How could that work? This hydrogen could bond right there, right? This hydrogen could bond right there, and what actually happens is you got an oxygen, and now 1 hydrogen comes floating up, and it goes, hey, we can make a bond here if I share my electron and yours. And then what happens is this electron that originally belonged to oxygen and this electron which originally belonged to hydrogen, they spend equal amounts of time, if it's a nonpolar bond, around both of the atoms. They spin around both of them, and that's what holds the whole thing together. So then the other hydrogen would go over here, share its electrons, and now, here's the beautiful thing about the water molecule, is once this bonding has happened, remember the octet rule? Everybody wants to have 8 electrons. Now, all of a sudden, oxygen thinks it has 8. Because it had 6 of its own, right? Those 2 were its own, those 2 were its own. That was one of oxygen's, and that was one of oxygen's. Now that it's sharing this one and this one, it is sharing them with hydrogen, and oxygen now believes, or feels like, is at the lowest energy state, which means it has 8 electrons. Hydrogen is also pretty darn happy, and hydrogen is full with only 2 electrons. How come hydrogen is full with only 2 electrons? It's got the very small shell, right? And it's only got one shell. So to bond hydrogen to other things, you can only bond hydrogen in one spot, right? Hydrogen's kind of like a one-armed guy, right? Can only hold on with one arm. You can never put hydrogen in between molecules and bond things together using hydrogen in the middle, because hydrogen only has a single electron, meaning it can only bond one place, right? This is something that is polar covalent. And the reason this is polar covalent is if we look at electronegativity on the periodic table, what's the trend for electronegativity, which is also the same as ionization energy? It's opposite of size, right? So it goes in this direction and in this direction. And the most electronegative element of all is fluorine. So I'm going to put the crown on fluorine, because that's the most electronegative element of all. So if we look at oxygen and hydrogen, here on the periodic table, there's oxygen, hydrogen's over here. Who's going to be more electronegative, hydrogen or oxygen, based on that trend? Oxygen's going to be way more greedy. So what that means is oxygen is more electronegative. What that means is it has a higher electron affinity. It attracts and pulls on those shared electrons harder than oxygen does. So it's sort of like in the bond here between hydrogen and oxygen, oxygen is holding those electrons real tight right up next to it. And on the other side, hydrogen is kind of holding them way out here because it's not as electronegative. So what that means is it creates a polar molecule. This side of the molecule where the electrons are all by themselves and sticking out is kind of negatively charged, so you can put a negative and a parentheses around it. This side of the molecule where the hydrogens hang out is positively charged, and that's because these electrons are pulled, the electrons that are shared are also pulled from the hydrogen closer to the oxygen. So polar covalent bonds are when the electronegativities between the atoms involved in the bond is unequal, and it causes an unequal balance of the electrostatic charges. Nonpolar covalent bonds are between either elements that are the same polarity, for example, like N2 or O2, right? N2 looks like this. We'll do the Lewis structure for that a little bit later in class today, but that's what N2 looks like. O2 looks like this because of the way that it's bonded. These are both nonpolar because they are both the exact same electronegativity. They're also what we call linear molecules. They're straight back and forth. And so there can't be unequal sharing of the electrons between the atoms that are sharing. See, here they're sharing 6 electrons. Here they're sharing 4. You can also get a nonpolar covalent bond if the molecule is symmetrical and it has uneven sharing bonds. For example, best example I can give you is CO2. Carbon, you see I made a double bond here in the model to oxygen, double bond to oxygen. Now if we look at the periodic table, who's going to be more electronegative, carbon or oxygen? Oxygen is going to be more electronegative, right? Because it's further to this side, there's carbon, there's oxygen, and electronegativity increases left to right. So since oxygen is more electronegative, the electrons are going to be pulled in this direction, but because it's a very symmetrical molecule, and the electrons are pulled equally away from the center, symmetry cancels out the polarity. So even though the bond is polar, right, this bond is unequally shared, the entire molecule itself can be non-polar. Okay? Now this will make a little bit more sense, this idea of polarity, once we get into actually drawing the Lewis structures. All right, we're not going to talk about bond energy yet. All right, Lewis structures. Let's see, what does it tell you here? You know, there's the rules, and hopefully you all printed out the PowerPoint because it's super helpful to have the rules available to you as we're going along with this. But what I'm going to do is I'm going to use the rules as a backdrop. So if you have the rules, take them out, and I'm going to use the rules as a backdrop to go through some molecules and how to draw these Lewis structures, all right? So the first rule says you're going to calculate the total number of valence electrons in the molecule. So what you do is you look at it and you say, all right, this one, like for example, let's just start with one of the examples. Our first example would be CH4. So let's just start with CH4, and we'll use the backdrop of the rules. All right, so if we look at CH4, I already showed you this molecule, methane gas, fart gas, things that cows and termites make a whole lot of. So rule number 1 says you count the number of valence electrons in the whole entire molecule. So we got to do one atom at a time. Carbon on the periodic table is in group 4, so how many valence electrons is carbon going to have? 4 valence electrons, so we put 4 down, that's the first 4. Hydrogen, because it's in group 1, has how many valence electrons? A single one, but there's 4 of them, so each one having 1, I have another total of 4 valence electrons. Now I'm not counting up the total electrons, only the valence electrons, and that's why it's important that you know that the representative elements, the group number is the same as the number of valence electrons. So I have a total of 8 valence electrons. So that's step number 1 in my list of rules, okay? If we had something that had a charge, like a negative charge, we are going to add an electron because that negative charge means it has one that it's not supposed to. If it has a positive charge to it, we're going to subtract 1 because that means that it has 1 less than it's supposed to. Then you're going to arrange the molecule around the central atom. And the central atom is most likely to be carbon, nitrogen, or oxygen in that order. So carbon is most likely, nitrogen is second most likely, oxygen is third most likely. Before we use that information, let's look at why that's true. Why is carbon, nitrogen, and oxygen most likely? Let's do the Lewis structures for each of these. Carbon, nitrogen, oxygen. How many valence electrons does carbon have? 4. 1, 2, 3, 4. How many opportunities to bond does carbon have?
4.
4. They used to call organic chemistry the study of carbon-based compounds. So if you take organic chemistry, it's all about carbon, because carbon makes everything that is life, there's some kind of carbon in it, right? Nitrogen has how many valence electrons? So 1, 2, 3, 4, 5. Now how many opportunities to bond does nitrogen have?
3.
Only 3. So more valence electrons does not necessarily mean more opportunities to bond, right? Oxygen has how many? 1, 2, 3, 4, 5, 6. How many opportunities to bond does oxygen have? 2. So first most likely to form bonds is carbon. First most likely to be the central atom is carbon. Second most likely to be central atom is nitrogen. Third most likely to be central atom is oxygen. Now that's a general rule, and sometimes there's molecules that don't have one of these in it, and you got to kind of work on that direction. All right, so back to our molecule of methane. Based on the rule, which one's going to be the central atom here? Carbon. So we'll put carbon in the middle. Okay. Now we're going to distribute the remaining atoms around so it's as symmetrical as possible, and we're going to use a bar or a stick to represent a bond that's formed between the central atom, the thing in the middle, and the peripheral atoms, the things on the outside. So I'm going to put H, 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 right? Put a bar in between each one, and each of those bars represents how many electrons? 2. So 2, 4, 6, 8 I had to use to make my molecule. So I have none left, but that turns out to be pretty handy and perfect because now carbon thinks it has how many electrons? 8. Carbon is its lowest energy state. Carbon is going, woohoo! Hydrogen thinks it has how many? 2. So hydrogen's pretty happy too. This molecule is now a whole lot more stable because of the fact that everybody has the octet filled. And once again, hydrogen doesn't always have the octet because it only has 2. All right, so we already did rule number 3, which is we're subtracting 2 valence electrons from the total for every bond, and then you distribute the remaining electrons so that the octet rule is followed except for hydrogen. Rule number 5 is a caveat that we'll come to when we need it. Let's do some more of these. Let's do NH3. We'll do a little structure for NH3. All right. NH3. Does anybody know the common name for NH3? I use it in my mop water to clean my kitchen floors. Ammonia. Ammonia is NH3. That's the common name. That's not the IUPAC name, right? All right. So nitrogen has how many valence electrons? 5. Hydrogen has 1 each, and there's 3 of them, so that's 3. They don't always have 8. It's just the simple molecules that I like to start with have 8. So we got 8. Who's going to be the central atom between nitrogen and hydrogen? Nitrogen. Put nitrogen in the middle. We're going to distribute the hydrogens as symmetrically as possible around. I'm going to go 1, 2, 3. How many electrons do I need to subtract now from my 8 to account for the bonds I just made? -6, that means I got 2 left over. If we look back at the rule and distribute the electrons, what do I do with the remaining ones? I got to make everybody follow the octet rule, right? So what am I going to do with those last 2 electrons? Keep in mind, what does nitrogen look like by itself? How many opportunities to bond does it have? 3. I'm just going to put those 2. And remember, they can't bond to anything else. And you can't do this. You can't do like 1 here and 1 there. They have to be paired. No bueno. We want them paired there. And that shows that we got a pair of electrons there, and that's going to turn out to be super important in just about 10 minutes. So make sure you keep the paired non-bonding electrons by themselves. Now, they're going to ask you questions in lab. They say, how many bonded pairs are around the central atom in methane? How many bonded pairs of electrons are around carbon? 4. Are there any non-bonded pairs? No non-bonded pairs. Ammonia. How many bonded pairs are around the central atom in ammonia? 3. How many non-bonded pairs? 1. There's 2 total electrons, but it's 1 pair. And we talk about pairs generally in chemistry. All right, let's get a nice molecule. Gotta draw. Good old H2O. All right. H2O. All right. How many valence electrons does oxygen have? 6. How many does hydrogen have? 1 each, and there's 2 of them. So once again, they don't all have 8. It's just I'm doing the simple molecules first to give you guys the examples. Who's going to be the central atom here? Oxygen. So I'm going to put hydrogen there and another hydrogen there. How many am I going to subtract from my 8 for the bonds I just made? 4. So I got 4 left over. What am I going to do with those 4? And that makes sense, right? Because the way oxygen looks, it's got those 2 and those that are opportunities to bond. Now, if I ask you the question about water, how many bonded pairs are around the central atom in water? 2. How many non-bonded pairs? 2. Very good. All right. And CO2. Now is where we're going to start getting into some of the caveats. Let's look at CO2. Carbon has how many valence electrons? No. 4. Oxygen has how many? 6, and there's 2 of them. So 12. All right, told you there weren't always going to be 8. So we got 16 valence electrons to distribute. Who's most likely to be the central atom? Carbon. So I'm going to put carbon in the middle. I'm going to put oxygen on one side because nature loves symmetry, right? So I want to put 1 oxygen on each side. How many do I subtract now from my 16 for the bonds I made? 4. So that means I got 12 left. All right, I'm going to do the next part in pencil. We're going to look at each of these atoms individually. Oxygen here thinks right now it has how many around it? 2. So it needs how many more to achieve the octet? 6. So it needs 6 more. So I'm just going to put a little light 6 there to kind of keep my bookkeeping in order. This oxygen is in the same boat, right? It also thinks it needs 6. Carbon, on the other hand, what's carbon's ideas about how many electrons are around it right now? Nope. 2 there makes 4. So carbon's impressions are that it only has 4. So how many more does carbon need to achieve the octet? 4. All right, so I need 6, 12, 13, 14, 15, 16. Yikes-a-roo. I got a problem. All right, our rules. Rule number 5, if there are insufficient electrons, which is what we have here, we don't have enough to go round, you double or triple bond the atoms. Now I want you to add a little note to that. You must double bond everything before you start tripling. You can't have a triple and a single, right? You have to have 2 doubles before you add a triple. So you have to double things first. I also would caution you to double bond one at a time and see what happens. All right? You don't automatically start slapping double bonds on everything because you don't have enough electrons. Let me show you how that looks. Here, I'm going to say, all right, I need a double bond because I don't have enough. I need 12, 16. I've only got 12. So I'm going to put a double bond there. So now I have to account for those electrons I just used. So how many should I subtract from my 12? Minus 2, I got 10 left. Now let's reassess the situation and see how much we think everybody needs. I'm going to leave the little circles around the atoms. This oxygen needs how many more? 6. Now carbon has a different impression than it did a few minutes ago. How many more does this carbon need? This one only needs 2, and this oxygen now only needs how many more? 4. Does everybody see that? That's important to be able to recognize that. You don't need your calculator for this. So I need 6, 10, 12. I only have 10. So what should I do? Double bond the other side, right? So we're going to do double bond there. I'm going to subtract 2 more for the bond I just made. I got 8 left over. I'll just scribble those out. All right. Is carbon happy now? Carbon is ecstatic. Carbon's going, yeah, I'm at the lowest energy state. What about oxygen? How many more does oxygen need? 4. I'm going to put them as pairs. How come I'm going to put them as pairs? How come I'm going to put them as pairs around oxygen here?
Because there's already 2 bonds.
Right. Those are where the bonds are happening. Those are the non-bonded electron pairs. You have to show them as pairs. All right? Same thing with this oxygen. 1, 2, 3, 4. 2, 4, 6, 8. Voila. Isn't nature wonderful? Follows all these wonderful rules. Let's try some that are ionic charges in nature. Let's look at something like NO3, which is the nitrate polyatomic ion. Once again, I'm going to ask you to start memorizing these polyatomic ions and make your life easier, and you'll get better grades on your exams. All right. Nitrate, there we go. All right, so N has how many valence electrons? 5. Each oxygen has how many? 6. There's 3 of them. 18. And then what do I do with that negative charge? Add 1 more. Right? All right, so 8 and 1 is 9, 10, 14. I got 24 valence electrons to distribute. Who's going to be the central atom? Nitrogen's going to be in the middle. I'm going to add oxygens around. How many do I need to subtract from my 24 for those bonds I just made? 6. That leaves me with 18. All right, let's assess our situation here. Think about what each of these atoms has. How many more does this oxygen need? 6. How about this one? 6. How about this one? Okay, now think before you answer. How many more does nitrogen need? 2. You guys are getting it. Good job. All right, so let's see what I got. 6, 12, 18, 19, 20. Oopsie. I only got 18, so what do I do? Double bond. I'm just going to randomly pick one of those, and I'm only going to double bond once. Now I have 16. Now let's reassess how many each of these things needs. How many does this oxygen need now? 6 still. How about this one? 6. How about this one? 4. And nitrogen needs 0. None whatsoever. Right? All right, so 6, 12, 13, 14, 15, 16. I'm going to put them like this, in pairs, pairs, pairs. Let's do one that's positively charged. Ammonium is, bless you, is NH4 plus. Is ammonium. It's a positively charged ion. All right, how many valence electrons does nitrogen have? 5. Each hydrogen has 1. There's 4 of them. But now, what am I going to do with that plus? I got to subtract 1, right? So 9 minus 1 is 8. Who's going to be the central atom here? Nitrogen. So we've got the perfect molecule now. Ammonium is completely balanced. It's got all of its electrons, right? Okay. Let's see. You know what? We didn't discuss resonance. Let's talk about resonance real quick. Almost forgot that. That's why these PowerPoints are helpful for me. Resonance. This molecule here exhibits a phenomena we call resonance. So let's write that down, resonance. What that means is this double bond is not always in that location. In fact, in a single second, that bond can move there, there, or there, and in fact it actually moves round and round multiple times in a single second. It never stays in that same location. Sort of like if you were playing the guitar. If you've ever seen anybody playing the guitar, it's kind of a cool thing. What happens when you're playing a guitar, I'm going to use my really bad artwork here to draw a guitar. And there's the thing, there's the frets, right, that you make the strings tighter on. And you got strings that go down through a hole, and they vibrate the string and over the hole, and it makes sound, right? Okay, so when I pluck one of these strings, what happens to it? Back and forth, right? So if I'm looking at just the string, it goes back and forth this way, which makes the sound. You know, the vibration is what makes the sound. So we pluck the string and it goes like that a whole bunch of times, right? That's the same thing here. It's sort of like it goes boo, a whole bunch of different times in a single second. So we can have what we call 3 resonance forms of this molecule, which would be that one that I have right there. It could be that one, or it could be that one. So we would say this has 3 resonant forms, meaning since there is a double bond and 2 single bonds, that double bond can move amongst the 3 different locations, and you have resonance amongst the double and the single bonds. Here they have a sulfur trioxide molecule, and it's very similar in structure. It also shows resonance. We just did NH4. There's a good one, CO2, that you can discuss. All right, now, before we go on, what I want to do is I'm going to show you now some really cool stuff that's going to help you with lab next week. And it relates to the molecules we've already done and what they look like in reality. All right, let's get my molecules up here, take a look. Okay. Now we're talking about individual molecules. Once they've bonded together, you know the basic rules on how to draw a Lewis structure. The thing is, with these Lewis structures, the way they look on paper is not the way they look in reality. This is more like what they look like in reality. You're going to be using these molecules and putting these molecules together in lab next week. So you have to know how to draw the Lewis structures first. And then you got to put them together and decide on what the molecular geometry looks like, okay? So now we're going to talk about molecular geometry by molecule. So if we look at the individual molecules, for example, if we look at something like, well, let's start with something like CO2. Okay, CO2 molecule here. This molecule is something that we call linear in nature. Why do you suppose it's called linear?
It's a straight line.
It's a straight line. So this molecule, the geometry is linear. All right. If I wanted you to tell me what the angle, the angle between these was, right? If I said, what's the angle, and this is CO2, what's the angle between the oxygens? 180 degrees, right? Okay, so it's a linear molecule. Fairly easy. All right, that's one thing. This one is, let's see what we've got here. I know I drew this one. Here it is. Actually, I should have red ones here and here. Get the red ones out so we have truth in representation here. Losing atoms and replacing them. You know, these molecular model sets you're going to be using next week cost $65. And I always wondered why they were $65 because my sons had Tinker Toys that were much cheaper. And it's because they have relative sizes, like hydrogen is a much smaller atom than oxygen, so they make them small. And they also make the little atoms and molecules with the correct number of holes that you need to plug them into other things. Like this black one has 4 holes, so what do you suppose this represents? Carbon, because it's got 4 holes. This is hydrogen, it only has 1 hole. This is a halogen, how many holes does it have? Halogen like fluorine? 1, 2, 3, 4, 5, 6, 7. How many holes should fluorine have? A single hole. It's also relatively small. So that's why it costs $65, because they've got the right number and they look like it. All right, this is NO3. So there's my double bond. See the double bond that I made? And this geometry on this molecule is a little bit different. This geometry we call trigonal planar. Trigonal planar is this molecule.
So that would be anything with the nitrogen.
No, it's the shape. Has nothing to do with the atoms that are involved. We're just looking at shapes now. So this is only shape. This is linear shape. This is trigonal planar. Now, the reason that it's trigonal planar is, look, it's in a plane, right? It's flat on the top, it's flat on the bottom, and there's 3 things sticking out of it. So what do you suppose the angle between these is? If it's 360s all the way around, each one, no, not 130, 120. Geometry was never my favorite topic. I always hated the proofs. You know, if you're going to do math, give me an algorithm and a formula and let me go. Don't tell me there's 10 different ways to solve this darn thing. Proofs made me crazy in geometry. You guys remember that do they still do that? Do they still make you do that in geometry? Oh, I hated that. All right, that's trigonal planar. We got to blame the Greeks on that. They're the ones that invented geometry. All right, this one. Does anybody know what this shape is called? Tetrahedral, right on. All right, so tetrahedral. Let's look at a tetrahedral molecule. I know I drew one already. Where's tetrahedral? Tetrahedral. Here it is. Here's a tetrahedral molecule. This stuff right here, the methane gas, right? Now, does the tetrahedral molecule on paper look the same as a tetrahedral molecule in space?
No.
No, on paper it looks like this angle is how much? 90 degrees. This is not a 90-degree angle. Turns out, tetrahedral, the bond angle, and these are angles, and these numbers you need to know, this is 109.5 degrees, not 90. On paper, the way you draw the Lewis structure, it looks like 90, because it's flat, it's two-dimensional, right? But here in space, it's not. It's 109.5, and that is the angle between all of the different parts of the same tetrahedral molecule. Okay? We can modify the tetrahedral molecule. Sometimes you lose one, like this molecule, NH3, right? We're going to say that's the nitrogen in the middle now, even though it's really black like carbon, we'll pretend it's nitrogen. And what happens is now we don't have an atom on the top. I'm going to leave the stick there because what does the stick represent? The 2 non-bonded electron pairs, right? So we have to understand that that's a big negative thing sticking out on one side of the molecule that's going to make this molecule polar and unbalanced, all right? So this particular shape is called trigonal pyramidal. Trigonal pyramidal. And now what happens is these pairs of electrons here and here and here, the bonded electrons, have a smaller, what we call lobe of repulsion. All right, what's a lobe of repulsion? When you have two electrons in a subshell. We have to think back to the last chapter on the periodic table. Remember energy levels? Subshells are the way that they spin. If we're talking about S spinning electrons, here's the nucleus, or here's two atoms joined together, right? They're spinning in a circular pattern, right, around them. So what happens is the lobe of repulsion, okay, here's the, we'll look at the nitrogen. Nitrogen and hydrogen. This lobe of repulsion here that holds these things together is relatively small. And the lobe of repulsion is caused by one electron spinning in one direction and one electron spinning in the other. It sort of looks like a balloon. If you blew up a balloon and you stuck it onto the nitrogen, the area where the electrons would be this lobe of repulsion that holds the hydrogens. This, the non-bonded pairs, have a larger lobe of repulsion, which means what happens is when this atom has another, or this molecule, has another atom at the top and it's perfectly symmetrical, it's nonpolar, right? I lose that one, I still have that negative electron cloud sitting up there. It creates a larger lobe of repulsion, and what it does is it pushes these down a smidge more. And now the angle here, where in a normal tetrahedral molecule it's 109.5, this decreases to 107 degrees. Okay, so now, because this is exhibiting a larger lobe of repulsion, it's pushing away these other atoms away from it. This big negative cloud of non-bonded electrons, it doesn't have anything bonded to it, is pushing these down, and so it takes this angle that in the past was 109.5 and it smooshes them closer. See how it's smooshing them? Because I'm pushing it down away from it, it makes the angle decrease. All right? And the last one is our friend water. Water, if I take off one more of these atoms on the outside, now it looks like water, right? Because I've got a hydrogen there, my oxygen's in the middle, and I still have these two areas of non-bonded electrons depicted in my Lewis structure by here and here. So around oxygen there's a lobe of repulsion there, a lobe of repulsion there, and one there. So the way that the molecule looks just based on its electrons is tetrahedral, if you just talked about the electrons, but that's not the way the molecule is. Water molecule is actually something we call bent. So this one is bent. This particular water molecule, or this particular molecule, the water molecule is bent. And that's because if it had had these two atoms hooked up here, right, everything would be easy peasy, it would be all very symmetrical, but since those are missing, I've got a big giant cloud of negativeness here, another big giant cloud of negativeness here. It takes these two and pushes them even closer. So instead of 109.5 or 107, the bent angle, this one goes down to about 103.5 degrees. So every time you lose another one of the atoms in the molecule, it decreases the angle that you have. So those are the shapes you need to know. We've got linear, trigonal planar, tetrahedral, trigonal pyramidal, and bent. Okay, those are the shapes you need to know. Now we're going to talk about them in terms of electron geometry versus molecular geometry. All right, so electron geometry versus molecular geometry. All right. Electron geometry is just the geometry that the electrons are creating on their own without taking into account what's bonded to them. So you're just looking at the lobes of repulsions on an electron. So if we look at water molecule, electron geometry of water molecule is, now how many pieces are around it? How many lobes of repulsion? No, 1, 2, 3, 4. So the electron geometry is tetrahedral. Meaning, because there's a pair there, even though they're not bonded, another pair there that's not bonded, a pair there that's bonded, and a pair there that's bonded, if we just look at what the electrons are doing, the electrons are doing a thing that is tetrahedral. Molecular geometry for water is not tetrahedral, it is bent. Let's look at another one. We'll pick this one. You guys remember what this one was supposed to represent? NH3, I believe it was, ammonia, right? Right, NH3. NH3 has how many lobes of electrons sticking out from that central atom? 4. 1, 2, 3, 4. So if it has 4 lobes of electrons, what's its shape? Tetrahedral. NH3, however, the molecule is different than the electron, so the molecular geometry of NH3 is it's trigonal, pyramidal. Let's go back to our original CH4 molecule. What's the electron geometry of this one? Tetrahedral. CH4. What's the molecular geometry of this thing? Tetrahedral. All right, so let's go back and look at these things individually now. Let's start with CH4. Okay, let's start with CH4. We need to discuss the polarity of this molecule. This molecule is super symmetrical, right? Looks pretty even, Steven, all the way around. Even though this bond is going to be polar. How come this bond is polar between the hydrogen and the carbon in CH4? Who's more electronegative? Is it the carbon or the hydrogen? Carbon is a lot more electronegative than hydrogen is, so it's going to be pulling those electrons tighter towards it, but it's pulling it in a very symmetrical way. It's pulling it even, Steven, all the way around. So this is a and you need to know this for the lab, polar molecule. And that is super important when you get into organic chemistry. You have to know how to do these things, because organic chemistry, the very first thing they look at is it polar or is it not polar? And that dictates a whole lot of the physical and chemical characteristics that elements have. All right, if we look at NH3, I'm going to take off one of these atoms, right? Now we have ammonia, which has a non-bonded pair of electrons there. So that's going to be the N. The black, we're going to represent the N. The H's are here. Who's going to be more electronegative in the bond between nitrogen and hydrogen? Nitrogen is going to be a lot more electronegative, so it's a very polar bond. So those electrons that hydrogen and nitrogen are sharing are being pulled a lot more towards the nitrogen in the middle, but then we also have this big negative lobe of electricity and of electrons here. So is this going to be a polar or a non-polar molecule? That's polar, so this one is polar molecule. And finally, let's look at water. Take off one of the water atoms. Now it's tetrahedral electron geometry, bent molecular geometry. Carbon is going to be a lot more, or excuse me, oxygen is going to be a lot more electronegative than the hydrogens are, so it's pulling the electrons in that direction. But then we also have 2 enormous lobes of negativeness that don't have anything to balance them out. So this whole part of the molecule is very negative. This whole part of the molecule is very positive. So water is super duper polar. Right? You guys are probably old enough to remember Barney, right? Remember super duper? Super duper. I always like that word. Super duper. Super duper polar. That influences a whole lot of the chemical and physical characteristics. The boiling point of water is so high because it's polar. Water, the density of ice is less than water because it is so polar. Water is what they call the universal solvent. It dissolves almost anything because almost everything on the planet is a salt because it is polar. If water was not polar, we probably could not have climbed out of the primordial soup and become humans. Honestly, it's because water is polar. That's why they think that when they're looking at other planets, if they have water, then there's a much better chance of life. But that's because we consider our form of life carbon-based as having water and being essential. What if there's another form of life that's maybe nitrogen-based rather than carbon-based, and they can live on ammonia gas? Right? Wouldn't that be cool? So, never know. Never know. Any questions? This is a lot of information to digest. Yes?
So for the Lewis structure that you were showing with ammonium,
Mm-hmm.
why was the nitrate, why could you when you said that beforehand, nitrate only had 3 opportunities.
Okay, so let me go back and make sure I understand your question, hon. So we're talking about NH4 or CH4?
NH4.
Or it was actually NH3. NH3. So now what was the question?
It was NH4 because you.
It was NH4 plus.
Okay, that's right. All right, so that's a different animal. NH4 plus. Now what was the question?
Yeah, so you showed it bonded 4 different times with each of the hydrogen atoms, but you said nitrate only had 3 opportunities to bond, right?
Nitrogen, not nitrate.
Well,
Nitrogen,
So,
generally, now that raises a good question. Chemistry is a lot like algebra because we use a lot of math. In algebra, though, you get a set of rules and it always applies, and if it doesn't apply, then it's not a rule anymore. In chemistry, we give you a set of rules and then we talk about all the caveats. So they don't always apply. The rules, as I'm giving you them today, are more like guidelines. So generally, nitrogen only has 3 opportunities to bond, but in special cases, it can bond a 4th time. But that's a great question. Somebody else had a question over here? Yes.
So when we talk about the geometry problem,
Electron or molecular geometry, and each of those terms will apply. Sometimes they're the same. Let me finish this sentence before you finish your question. If the electron and molecular geometry are different, generally the molecule's going to be polar. That's a good thing to write down. If the electron and molecular geometry are the same, then it's generally nonpolar. I'll say it one more time. I'll give you an example. If the electron and molecular geometry are the same, right? CH4, electron and molecular geometry were the same, it's nonpolar. If the electron and molecular geometry are different, then it's generally polar, and that's because you usually have non-bonded electron pairs around the central atom. And that, not always, but most of the time, makes them polar, if you have non-bonded electron pairs. Okay, now I totally interrupted you with your question. Ask me your question again.
but for those models, I sort of have to know the degrees for all of them.
You should, well, if you look at the molecule itself, right, and you know a smidgen about geometry, you can say linear is 180, right? Trigonal planar is 120, right? Tetrahedral is 109.5, right? If all of them are bonded, it's 109.5 between all of them. If it's trigonal pyramidal, it goes down from 109.5 to 107. If it's bent, it goes down from 107 to, what did I say, 10 something? Okay, it goes down. Okay?
It starts at 180.
Actually, it starts at 109.5 if you're talking about tetrahedral. Tetrahedral. Okay? Good questions. All right, you guys can get started on the lab on molecular geometry too over the weekend. I'm going to download this video. I have another one from my 151 class that covers the same stuff. Have at it. No, but I will be here on Friday.